Have you ever just stopped and wondered what sound actually is? I mean, how does the noise from a speaker travel all the way through the air to get to your ear? It really does seem kinda like magic, but I promise you it's pure physics. And today, we're gonna uncover the one fundamental secret behind all of it: vibration.
So, to get to the bottom of this, we're going to focus on one central mission, one single question that's going to unlock everything else for us. And that question is, can anything, I'm talking a whisper, a huge explosion, a simple musical note, can anything produce sound without vibrating? Let's go hunt for the answer. Okay, part one of our investigation takes us right to ground zero, the source of the sound itself. To answer our big question, we have to figure out where every single sound, from the tiniest little whisper to a massive drum beat, actually begins. To find out, let's start with a really classic physics experiment. Imagine you've got a tuning fork. You strike it with a rubber hammer, and now bring it close to your ear. You can hear that clear, humming tone, right? But here comes the really interesting part. Now, gently touch one of the prongs. What do you feel? It's not still, is it? It's buzzing, it's trembling like crazy. That feeling? Well, that's our first major clue.
Okay, so hearing the hum and feeling the buzz, that's some pretty strong evidence, right? But, for a scientist, that's just not enough. We need to actually see it happen. So the next challenge becomes, how in the world can we make this invisible vibration visible? And here's how we do it. It's such a brilliant, simple proof. Imagine we attach a tiny little wire to the tip of that vibrating tuning fork. Now we drag it across a piece of smoked glass. And look at that. It etches a perfect wavy pattern. But what happens if we do the exact same thing with a fork that's totally silent, one that isn't vibrating? You just get a simple, straight line. The connection here is absolutely undeniable.
So, the evidence is, well, it's crystal clear. That wave pattern only appears when we hear the sound. So, what does that prove? The sound has to be produced by the vibration. We've just cracked the first part of our mystery. To make sound, an object absolutely positively must vibrate. So let's lock in the official term for this, because this is a big one. A vibration is an oscillation, which is just a fancy way of saying a rapid back and forth movement around a central point. That buzz you felt on the tuning fork, that's exactly it. And trust me, this is a key term you are definitely going to want to remember for your exams.
And this isn't just about tuning forks in a lab. This is happening everywhere. Just think about it for a second. The string of a guitar blurring as it moves back and forth, the skin of a drum rippling up and down when it's hit, the cone of a speaker pulsing in and out. They are all perfect, everyday examples of vibrations creating the sounds we hear.
Okay, time for a quick question for you. Which part of your very own body is creating a vibration to make sound? Go on, try humming and put your fingers right on your throat. You feel that? That is your vocal cords, rapidly oscillating to create your voice. Pretty cool, huh? All right, so we've cracked the code on how sound is born. It all starts with a vibration. But you know what? That's only half the story. Now we get to part two. How does that vibration travel from the source, say, across a room, and all the way into your ear? This journey is just as fascinating as the origin. Now, to understand this journey, we first need to know what it's traveling through. And that brings us to another one of those super important exam keywords, the medium. The medium is simply the stuff that sound uses to travel. It could be the air all around us, the water in a swimming pool, or even the solid wood of a desk. So, how does sound actually get through this medium? Well, logically, it can really only be one of two ways. Theory number one. The vibrating object is kind of like a tiny machine gun, shooting off these invisible sound particles that fly across the room and hit our eardrums. Or there's theory number two. The object creates a disturbance, kind of like a ripple in a pond, that travels through the medium. So which one is it? We can actually figure this out with a simple but brilliant thought experiment. Let's think about theory one. If a ringing bell were constantly shooting off particles, what would have to happen? Well, it would be losing mass, right? Over time, it would get lighter and lighter until it literally just vanished. And we know that doesn't happen, so theory one is officially busted. Well, that leaves us with only one possibility left standing. Sound has to travel as a wave, a disturbance moving through the medium. But what does that actually look like on a particle level? Okay, let's zoom in and see what's happening. Let's go back to our drum example. When you hit it, the drum skin vibrates, right? So as it pushes forward, it acts like a piston, ramming into the layer of air particles that are right in front of it and squishing them all together. This area, where all the particles are squished and crowded together, is called a compression. It's a region where you have high particle density and high pressure. This compression then shoves the next layer of air, which shoves the next one, and on it goes. But remember, the drum skin doesn't just move forward, it immediately pulls backward, and as it does that, it moves away from that first layer of air, leaving behind this empty space with way fewer air particles than there were before.
And this area of spread out low-pressure particles, it has a name too. We call it a rarefaction. And just like the compression, this rarefaction pulls on the particles in the next layer, and that effect keeps traveling outwards.
So what you get is this amazing chain reaction, a whole series of compressions and rarefactions traveling away from the source. But listen, here is the most important thing to get right. The individual air particles themselves are not flying across the room to your ear. Nope, they're just wiggling back and forth in their own little spot. It's the disturbance, the wave of energy, that travels from the drum to you. So now that we've really explored the physics behind all this, let's pull it all together. Right here, we're going to build the perfect exam-ready answer to make absolutely sure you can explain these concepts and score full marks when it counts.
If you get an exam question that asks you how sound propagates, here is your perfect 4-mark answer. Point 1. The source. It all starts with a vibrating object creating a disturbance. Point 2. Compression. As that object moves forward, it creates that high-pressure region. Point 3. Rarefaction. As it moves backward, it creates the low-pressure region. And finally, point 4, propagation. This whole series of compressions and rarefactions travels forward as a wave, carrying the energy along with it.
Now, here's a common point of confusion. Do the compressions move forward while the rarefactions move backward? The answer is a definite no. Think of them like the front and back of a single train car. The entire train, the whole disturbance made of these alternating compressions and rarefactions, moves forward together away from the source.
So, after all of our investigating, from tuning forks to drum skins, it all comes back to one simple, powerful truth. If you remember only one thing from our time today, make it this: no vibration, no sound. It is the fundamental secret behind every single sound you have ever heard and every sound you ever will hear.